Welcome to the deep dive. This is where we take really challenging source material, break it down, and hopefully turn it into something you can genuinely grasp. Today, we're tackling gravity, but not just the everyday pull keeping us grounded. We're going beyond that basic GMR2 idea. We're diving into the math behind differential acceleration. So our mission today, decode something called the gravitational tidal tensor. This is the math that explains, why black holes create spaghettification, and also why the moon, which is tiny compared to the sun, has such a big effect on Earth's tides. We've got the stack of pretty technical notes here detailing the derivation step by step. It looks dense, but the goal is, by the end of our chat, you'll really get the physical meaning behind all the symbols in that final formula.
Okay, so where do we start? The basic puzzle seems to be, if you have two particles falling towards, say, a planet, why don't they just fall together? Why does the distance between them change?
That really is the heart of it.
Yeah.
That is the tidal force. See, if gravity was perfectly uniform everywhere.
Like a constant pull everywhere.
Yeah.
Exactly. Then every single particle would accelerate in precisely the same way. Their separations wouldn't change at all. You'd feel weightless, sure, but no stretching, no squeezing. Tidal effects pop up because gravity isn't uniform. It changes with distance. The side of you closer to the Earth feels a slightly stronger pull than the side farther away.
Okay.
So we're not really studying the gravitational field vector today. We're studying how vec changes over small distances. That difference, that's the differential acceleration.
Right. So the sources set this up with a thought experiment. Two particles. One at position vec deck, the other just a tiny bit away at vec plus vec, and we need to figure out the tiny difference in their accelerations.
Precisely. And the key insight, because we're talking about a really small separation to vec, is that we can use a linear approximation.
Meaning the relationship is simple.
Yeah, for tiny changes, the difference in acceleration vec deck is basically directly proportional to the separation vec.
Yeah.
Think of it like zooming way in on a curve. It looks like a straight line.
Okay, that makes sense. We're just looking right nearby.
And if it's a linear relationship, well, then we can represent it mathematically. We need something that takes the input vector, vector, and gives us the output vector, vector. That something is a tensor. The sources call it a teller, rank 2 tensor specifically.
Got it. And the equation in the notes is $AIISOUD XJC. Dollars is like the conversion factor. It translates the separation distance into the difference in acceleration.
It connects them.
But why a tensor? Why not just a number or maybe another vector?
Oh, that's a really important point. It has to be a tensor because direction matters a lot. The direction of the separation v affects the resulting differential acceleration dv, but they don't necessarily point the same way.
How so?
Well, imagine two particles separated side by side, horizontally, relative to the mass pulling them. The tidal force might try to pull them radially apart, stretching them vertically, but also push them together horizontally.
So it's complex. Stretching one way, squeezing another.
Exactly. You need something more sophisticated than a simple scalar or a vector. A tensor, which in 3D is like a 3x3 grid of numbers, captures all 9 possible connections. How separation in x affects acceleration in x, y, and z, how separation in y affects acceleration in x, y, z, and so on.
So $2 holds the entire geometric picture of the distortion, the stretching, the squeezing.
Yes, and that's why it gets the name. Tidal tensor. It literally quantifies the forces causing tides and spaghettification.
Okay, let's move into the next section then. Defining $2 more formally, the notes bring in the gravitational potential, habitai. We know acceleration velar is the negative gradient of pi, so dollar nabla. How does $2 relate to Dillard?
Well, val is the first derivative of potential.
The slope, kind of?
Yeah, the slope of the potential field. Then the change in acceleration, didal, must come from the second derivative of the potential.
Change in the slope.
Exactly. That's the crucial step. Tellers is fundamentally about the second derivatives of Tillet. The formula they give is Tillier, Pellier, Pourchoi. Now, don't worry too much about the partial derivative symbols. Partial Killet. Conceptually, it means we're taking the derivative of the derivative.
What does that second derivative actually mean, physically? We know the first derivative, the gradient, is the force, the steepness. What's the second?
It tells you about the curvature of the potential field. Imagine that potential as a landscape, like a valley. The first derivative is how steep the valley walls are, right where you are.
Right.
The second derivative tells you if the slope itself is changing. Is the valley floor curving up or down? Is it getting steeper or shallower?
I see. It's about the shape, not just the steepness.
Precisely. If the field lines are converging, curving inward, that corresponds to a squeezing effect. If they're diverging, curving outward, that's a stretching effect. That's where the distortion comes from mathematically.
That's much clearer. It's the shape of the gravitational well, not just its depth.
That's exactly right. And the notes point out something neat that falls out of this definition. For most physical fields, the order you take partial derivatives in doesn't matter. Differentiating with respect to x then y gives the same result as y then x.
Okay.
Well, that means tergel must be equal to t or dollars. The tidal tensor has to be symmetric.
Symmetric, meaning the effect of, say, an x separation on y acceleration is the same as a y separation on x acceleration.
Yes, it tells us the twisting or shearing effects are balanced. The field itself doesn't try to introduce a net rotation on a small object, just distort it.
That symmetry sounds like it simplifies things.
It does. It ensures the forces are purely about changing shape, about relative motion.
Okay, so we have this abstract definition. Let's ground it. The sources calculate dollars for the classic case. Outside a spherical mass, $hours. The potential there is just phi matches gm dollars. First step is getting the field. We know that. It's basically the inverse square law, versus gm share 3. But the real meat is the second step, taking the derivative of the components to get the components of terg.
Right. TG is basically partial xj. And doing this calculation reveals the different parts of the tidal force. We have to look at the diagonal terms, CG and the off-diagonal terms, 1xj separately. Which one's first? Let's maybe start with the off-diagonal ones, where intolerance is not equal to J. These describe how a separation in one direction, say x, causes a differential acceleration in a different direction, like y.
So these are the shear or twist forces.
Exactly. If you have two particles separated along the x-axis, these terms tell you about forces trying to push them relative to each other in the y or z directions.
And the calculation gives TGD of 3gm frac I5 for 1 dextagle.
That's the one. TGGL 3gm frac j in 1 dexday.
Whoa, torredo dollars to the fifth power. Gravity itself is 102 under 2.
Right. The gravitational force drops off as 102 under 2, but the tidal force, the differential effect, drops off way, way faster as 105.5 in these shear terms.
That must be why tidal forces are so localized. They get weak really quickly with distance.
Extremely quickly. If you double your distance, the main gravity pull drops by a factor of 4. The tidal force drops by a factor of 2 under every $5, which is 32.
Wow. Okay.
That's why Jupiter, massive as it is, barely causes tides on Earth compared to our tiny moon. The moon is just so much closer. That 105 ideali matters enormously.
So these off-diagonal terms are twisting things.
Yeah, they represent the shearing stresses. Trying to sort of rotate a small object so its longest dimension aligns radially towards the mass dollars.
Okay, now for the diagonal terms. TDAC. This is where the separation and the differential force are in the same direction. Like separation along z causes differential acceleration along z.
Correct. And these are the ones you usually think of first. The pure stretch and squeeze. The formula here is TIGM left frac rac 1 right.
Okay, that looks a bit more complex. It's got two parts, one subtracted from the other. What's going on there?
This is spaghettification written down mathematically. Look at the two terms. The first one with the 3, 5, 2, har, 5, 5 is always positive. This represents a stretching force along the radial direction, the direction towards or away from dollars. It's strongest along the axis, pointing right at the mass dollar. It pulls the near side even nearer and the far side relatively farther.
So if you're falling feet first towards a black hole, that's the term stretching you head to toe.
Precisely. But notice the second term, GMR 303. It's negative.
Meaning it pushes inward.
Yes. It represents a squeeze in the directions perpendicular to the main stretch. So if you're being stretched radially along the z-axis, this term causes a compression, a squeeze, along the x and y axis.
Oh, okay. So you get pulled long and thin like spaghetti because you're stretched one way and squeezed the other way.
That's exactly it. Think of Earth tides. The water bulges out towards and away from the moon, stretched, but it's simultaneously squeezed inward from the sides.
So the tidal tensor isn't just one force, it's this whole system of pushes and pulls acting differently in different directions.
It describes a volume-preserving distortion, essentially. Stretching in one dimension requires compressing in the others. The full $3 times 3 matrix captures all of that.
The sources combine all this into one compact formula using something called the Kronecker delta.
Now, the delta is just mathematical shorthand. It's one if one diagonal terms and if one x83 for the off-diagonal. It lets you write the diagonal and off-diagonal formulas together.
But the physics is in those two effects. The 4-lever-dependent shear stretch and the 3-lever-dependent squeeze.
Correct. The key takeaway is the geometry. Mass dollar creates this distortion field around it.
Okay, let's just quickly revisit the relevance. That 4-lever dependence, it means tidal forces are usually tiny in everyday life, right?
almost always negligible, unless
Unless the mass in dollar is huge or the distance dollars is really, really small.
exactly. Think about approaching a black hole. The difference in gravity between your head and your feet, even over just a couple of meters, becomes enormous because torians are so small.
Yeah.
That 105 LR term blows up.
That's the spaghettification. The differential force becomes catastrophically large.
And this tidal tensor, derived just from Newtonian gravity and calculus, lets us calculate exactly how strong that force is. It gives us a precise measure of the physical distortion.
It takes us from just saying gravity is strong to quantifying the rip you apart stress.
So, stepping back, what have we really found? We've unpacked the math behind tidal forces for a simple spherical mass. And we see that gravity, when you look closely, is fundamentally about differences. It's about your motion relative to things nearby you.
It feels like we've described how mass distorts things locally, how it creates these stresses, almost like we're touching on space being distorted, but without using general relativity.
And you've hit on the perfect final thought. This Newtonian tidal tensor, $2, that we just worked through. It's essentially the ancestor, the weak field version of a much more famous object in Einstein's general relativity, the Riemann curvature tensor. When Einstein described gravity not as a force, but as the curvature of space-time itself, he needed a mathematical tool to quantify that curvature. And what does the Riemann tensor do? At its core, it describes the relative acceleration of nearby objects moving through curved space-time, exactly what our tidal tensor does in Newtonian space.
Wow, so they're directly related.
Deeply related. In situations where gravity is weak and speeds are low, the complex Riemann tensor simplifies down, and its key components basically become the components of the tidal tensor we calculated today.
So here's something for you, the listener, to think about. If our Newtonian tidal tensor describes relative motion due to gravitational force, and the Riemann tensor describes relative motion due to space-time curvature, does that imply that these tidal effects, this stretching and squeezing, are maybe the most fundamental, unchanging aspect of gravity, bridging the gap between Newton and Einstein? What does that tell us about the reality of that distortion? Something to chew on until our next deep dive.